Log on, tune in, find out. Another good idea from Cambridge.
So it's a great pleasure to introduce the first speaker of the morning session, Tudor Dimofte from Princeton, who is going to tell us about S-duality and mirror symmetry in Chern-Simons theory.
Thanks a lot. And let me also just thank the organizers for a really lovely conference and for inviting me to come. So the talk today is based on current work with Sergei Zhukov. Hopefully there will be a paper coming out soon. I'd like to discuss a topic that's probably a little bit unfamiliar in this audience, namely operators and wave functions in analytically continued Chern-Simons theory. Also sometimes called Chern-Simons theory with complex gauge group. And I'll explain in a second why this has anything whatsoever to do with derived categories. But very roughly, one can take a real three-manifold M, which for my purposes will always be the complement of a knot in the three-sphere, meaning that you draw a knot in S3, you thicken it a little bit and cut it out. And we'll take a gauge group that's typically a complex group, SL2C. And then Chern-Simons theory, some way or other, assigns a wave function to this manifold, and depending on this gauge group, that depends on two complex parameters, u and h bar. So h bar here is a complex coupling constant of the theory. And u parameterizes in a certain way boundary conditions of the theory at the knots. It's a parameter needed for the theory to be well defined. So these are boundary conditions. In fact, we'll see that u is an eigenvalue of an SL2C matrix. So this object ends up having two remarkable properties. One, it's annihilated by a certain operator, a certain difference equation, which looks like this. And so this operator is called a hat. It depends on the three-manifold M, and it's a polynomial in two non-commutative operators, L hat and M hat. And I claim that it annihilates this wave function, which I haven't defined yet. So here and for the rest of the talk, M or M hat, oh, should I? Yeah, thank you. M is always e to the u. So here, M hat just acts as multiplication by e to the u. Q is e to the h bar. And L hat shifts u by h bar over 2. So in physics, and probably also math notation, I'd write this as L hat is equal to e to the h bar over 2 d du. It's probably very small, but what I mean is that L hat acting on a function of u is f of u plus h bar over 2. Okay, so there's a difference equation for this wave function. And fact number 2, which ends up being closely related, is that both the wave functions and the operators have S-duality. What I mean by this is that, properly interpreted, the wave function at 2 pi I over h bar times u and negative 4 pi squared over h bar is equal to Zm at u and h bar. And this quantity, 2 pi I over h bar u, is going to be called u tilde throughout. So u tilde is 2 pi I over h bar u, and h bar tilde is negative 4 pi squared over h bar. So in a sense, this is a Jacobi-like transformation in that it inverts h bar, or often it's called tau, and it scales the Jacobi variable. So the wave function has an invariance property, and similarly, there's a dual difference equation. So there is a difference equation depending on L, M, and Q, and there's a dual equation, A hat, depending on L tilde hat, M tilde hat, and Q hat, which also annihilates the same wave function. And I really do mean that this is the same A hat. It's the same polynomial of non-commutative variables. It simply depends on different variables. So here, Q tilde. Q tilde is e to the h bar tilde. M tilde is e to the u tilde. And L tilde can be written in several ways. It ends up being shift by I pi. So it's e to the I pi du, but that's really the same as e to the h bar tilde over 2 du tilde. So they're completely dualized variables. Okay. So let me just say that for S-duality to work like this, so this is the S transformation going from z to z in the dual variables. For S-duality to work like this, it's very important that analytic continuation is done in Chern-Simons theory. In other words, that we don't have Chern-Simons with compact group SU2, which is most often looked at in math and physics, but rather Chern-Simons with something like gauge group SL2C. So for compact group SU2, so if we had taken SU2 theory, we'd find that both h bar and u are quantized. In particular, q e to the 2 pi I over k is the parameter appearing in Jones polynomials, in fact, in colored Jones polynomials. So SU2 Chern-Simons invariants are not complements, are colored Jones polynomials. And k is an integer. Moreover, u, right, so q is e to this, so h bar is 2 pi I over k, and u is I pi n over k, where again n is an integer, in fact a positive integer, labeling a representation of SU2. So if I use compact group and quantize the parameters, it makes absolutely no sense to try to invert them. This analytic continuation that I'm talking about, initially without any mention of S-duality, was introduced by Gukov 8 years ago and recently reconsidered in great detail in a paper of Witten's. Okay, now why do we care about this? Why do we care about this at this conference? Okay, we'll try to convince you. There's a little chain of dualities. So Chern-Simons, analytically continued Chern-Simons theory is closely related and in fact often equivalent to 4D super Yang-Mills theory. Topologically twisted versions of 4D super Yang-Mills, which is then in turn related essentially by Kapust and Witten and geometric Langlands to to two-dimensional topological sigma models. As an example, let me give you one precise chain of equivalences that demonstrates this. Witten recently, I think in his last paper, argued that 3D Chern-Simons theory on a manifold M, so the analytically continued version, and in fact on a closed manifold, because things get a bit more complicated if you look at knot complements. 3D Chern-Simons on a manifold M should be equivalent to Langland's twisted 4D super Yang-Mills on a 4 manifold that's M cross R plus. Or you can also make this work with M cross an interval. This allows you to reproduce various ingredients of Chern-Simons. So the simplest thing you can do is take M to be a surface C cross R interpreted as time. Then quantization of physical Chern-Simons theory on a surface cross R gives you the Hilbert space of Chern-Simons, a Hilbert space that should be canonically associated to C. Then over here, the 4D super Yang-Mills theory now lives on a surface, a 2D surface, cross R plus. And we can think of the surface as being very, very small and get an effective theory on R cross R plus. Or it's actually nicer for this example to think of R cross an interval. This effective theory is a 2D sigma model. From a world sheet, R cross interval, to a target space, which is the so-called Hitchin moduli space. Associated to the surface C and compact gauge group G, which for purposes of this talk is going to be the same as the space of flat complexified SL2C connections on the surface C. Since the world sheet in the sigma model has a boundary, so R is still playing the role of time, but its time space is an interval. So strings in this sigma model are stretched between two boundaries. In other words, between one brane and another on this target space. There should be, we need to define branes here, or choose branes here to give well-defined boundary conditions for the sigma model. It turns out, right? So world sheet kind of looks like this, and we need a brane here and a brane here. In a paper of Glukhoff and Witten, it was argued that if we choose a certain Lagrangian brane here and a certain canonical coisotropic A brane here, and look at an A model on this target space, then Hom B prime BCC, the space of strings stretched between these branes, or Hom in the Fukaya category, is going to be equal to this canonically quantized Hilbert space of Chern-Simons on C.
So the symplectic form is it real or complex? BCC is a complex manifold.
So this is hyperkähler. So I will give more details. Possibly this is a bit long of an introduction. So I'll do some things very explicitly later on. But this is a hyperkähler manifold. It has three real symplectic forms, and you're looking at an A model in one particular symplectic structure. Okay. So the hope, right? So this much, at least this board, even though I haven't explained it in detail at all, is well understood. The hope is that a picture like this can be used to interpret the S-duality that I mentioned in Chern-Simons theory, this inversion of H bar. And the rough idea is that S-duality in Chern-Simons should be equivalent to S-duality in Super-Yang-Mills theory, which should then correspond to mirror symmetry in this hyperkähler moduli space. The problem in making this work in practice is that the precise branes one has to choose are quite complicated objects to begin with, and then acting on them with mirror symmetry gets more complicated still. So the picture that is well understood is actually for quantization of Chern-Simons with compact gauge group. So this, in particular, this Hilbert space is going to be something finite dimensional, and then it's been computed as a Hom space between two branes. When you look at the analytically continued theory, things seem to work a bit differently. So for the rest of the talk, I want to give you a flavor of various ingredients in these that come into these constructions. On the Chern-Simons side, I want to say a bit of what these wave functions and operators actually are, and give some examples of S-duality, because you can actually write everything down. And on the sigma model side, I want to discuss one interesting class of Lagrangian branes that correspond, in fact, to the classical limit of these A hat operators, and how mirror symmetry acts on them.
Is A hat operator the non-commutative A polynomial?
Yeah. Yeah. Okay. So then let me start talking about Chern-Simons in more detail. So Chern-Simons is, well, first of all, it's a 3D topological quantum field theory. That, as I wrote over there, it takes a three-manifold M and a gauge group G, and spits out a partition function or a wave function that physicists would say is computed by a path integral, integrating over the space of all G connections on M of e to I over h bar times the integral over M of trace ADA plus 2/3 A cubed, the Chern-Simons form. The classical solutions of this theory, or the critical points of this exponent, are flat connections. In other words, curvature dA plus A squared is 0. So that's classical. At a quantum level, this partition function essentially lets connections fluctuate or deviate a little bit from flatness, or possibly quite a lot from flatness, and measures the strength of those fluctuations with h bar. A common situation, as I was saying before, is when G is a compact gauge group SU2, then you get Jones polynomials or Witten-Reschtiken-Tourev invariants of the three-manifold M. We want G to be complex, so we want GC to be well, we want the gauge group to be SL2C, and we want h bar to not be some quantized thing, but an arbitrary complex number. Moreover, we want to look at the theory on a knot complement. So So if M is a complement of a knot in, for example, the 3-sphere, it requires choosing some boundary conditions at the knot. The boundary of a knot complement, if we thicken the knot a bit and then cut it out, the boundary is a torus. Draw it roughly on the board. And good boundary conditions are fixed by choosing a conjugacy class for the holonomy of the connection. So the connection A, which this is a theory of. Choose a conjugacy class for the holonomy of A along a so-called meridian cycle of the torus. It's a cycle that kind of links the x-sized knot around a little loop. So I'm going to fix that the conjugacy class of that holonomy has eigenvalues m and m inverse, and since we're in SL2C, it could possibly be parabolic. And I think as I said before, m is always equal to e to the u. So u is the logarithmic holonomy eigenvalue, and then the partition function, the wave function z of that only depended on h bar before, now depends on h bar and on a complex parameter u. There's another interesting cycle on this torus, which is called the longitude. So this is the meridian. The longitude intersects the meridian once and is null homotopic, or null homologous in M. And we can fix that holonomy as well. Well, if we're just thinking about the boundary, we can try to diagonalize that holonomy as well. And that's going to have eigenvalues L and L inverse. Okay, so the meridian is a good boundary condition for Chern-Simons, but if we just look at flat connections on the torus and not the entire 3-manifold, you can actually choose both of them. And what I mean by that is, that the moduli space of flat connections, of flat GC connections on the torus, which is hom from pi 1 of the torus into SL2C, modulo conjugation by SL2C, is parametrized by these eigenvalues L and M. So the set of Lm modulo a residual Z2 Weil group quotient that inverts both L and M. And it's also very convenient to write it in terms of logarithmic coordinates as parameterized by two complex numbers u and v, where Z2 acts by inverting the sign of both u and v. So up here, m is e to the u, and L is e to the v. This thing is the classical phase space, the so-called classical phase space of Chern-Simons theory on a torus. It's called a phase space because it comes with a symplectic form. In this case, a holomorphic symplectic form induced from the Chern-Simons action, which in terms of logarithmic variables is just 2 dv du. A semi-classical state in Chern-Simons corresponding to flat connections on all of M, not just on the boundary torus, should be a Lagrangian submanifold in this phase space of the boundary. To put that into equations, So we start off with just looking at the boundary, and then we say that this boundary has to be part of some 3-manifold. That essentially means that we're no longer allowed to fix L and M independently. So we define a space Lm. Never occurred to me it would be confusing to talk about L and M and then call something Lm. As the space of flat connections on T2 that extend to be flat in M, or to be flat on M. And that ends up being cut out by a single polynomial equation in the eigenvalues L and M. And this thing is called the classical A polynomial of the knot complement. It a priori has nothing to do with Chern-Simons and was discovered completely independently in math. Okay, so for example, let's make this a little concrete. Let's take the unknot. The A polynomial of the unknot, well, it enforces the condition that a flat connection on kind of a little torus surrounding the unknot can be extended into the entire 3-sphere. Since the longitude loop is null homologous, and in fact, in the case of the unknot, it's null homotopic, that holonomy has to be trivial. The longitude loop is contractible. So the condition that a flat connection on the unknot extends to all of M is really simple. It's just L equals 1. If I take a slightly more complicated knot like the trefoil, well, it's slightly more complicated, but it's still nice. It's a torus knot. So A of the trefoil always has an abelian factor, which I'm typically going to ignore in this talk. I'll explain why that's an abelian. Well, maybe I won't explain why that's an abelian factor. Everything has a factor of L minus 1 for knots in the 3-sphere. So it's an L minus 1, which I don't want to look at, times L plus m to the 6. And getting even more complicated, can look at the figure 8 knot. So here it gets more non-trivial. It's m to the 4th L squared minus 1 minus m squared minus 2 m to the 4th minus m to the 6th plus m to the 8th L plus m to the 4th. Okay. So that's the classical story. Those describe classical flat connections. In order to quantize Chern-Simons theory, we want to turn this phase space of the torus into a quantum Hilbert space. The situation here with analytic continuation is a little bit funny, in that typically when you quantize phase spaces, you have a real symplectic form on them, and here we have a holomorphic symplectic form, essentially because we've analytically continued from a real situation. So what ends up happening is that quantization here doesn't exactly give you a Hilbert space. It gives you as best as anyone can tell, a vector space of holomorphic functions. So there's, in quotes, some Hilbert space corresponding to the torus, which consists of functions of half of the complex variables on that phase space. We'll choose them to be functions of U. And I want to think of them as holomorphic functions that are analytic continuations of functions in L2 of R. And I realize that's not a very precise thing to say, but it's the best I or anyone else can do at the moment. Anyway, so this is some vector space. And there's an algebra of operators acting on it. This algebra is generated by operators u hat and v hat that act on functions f of u. Well, u hat acts by multiplication, and v hat acts by differentiation. Such that their commutator agrees with the inverse of that symplectic form. So the inverse of the symplectic form with an extra factor of h bar. So v hat u hat should be h bar over 2. Similarly, we can exponentiate u hat and v hat and get operators L hat, which is e to the v hat, and m hat, which is e to the u hat, which also act on such wave functions. And then we might ask, well, we have a specific three-manifold here. This Hilbert space only depends on the boundary. So what comes out of the fact that the boundary is glued into a three-manifold? Well, what comes out is a wave function of the three-manifold. It's the object I already have written on the board. So we get a wave function in this quote-unquote Hilbert space of the torus. So function of u, and depends on an auxiliary or on a coupling constant h bar. And the classical condition that flat connections are specified by points on the zero locus of this A polynomial, that classical condition becomes the quantum equation A hat z is equal to 0, where A hat of Lm and Q is some quantization of this classical A polynomial. Now, quantization is easy to talk about, but very hard to do in practice often. In particular, the precise procedure for quantizing this A polynomial can get fairly complicated, and the ordering ambiguities that seem to appear in the quantum versions are pretty bad. So starting off with something like the trefoil, the A hat polynomial looks fairly nice. It's just L hat plus Q squared m hat to the 6. And it annihilates a wave function that's e to the 3 over 2 h bar u squared plus 1 over h bar 2 pi I plus h bar u. But if you start looking at something like the figure 8 knots or anything that's not a torus knot, it gets quite bad. So for example, the A hat polynomial for the figure 8 knot is q squared 1 minus q squared m hat to the 4th m hat to the 4th L hat squared minus 1 minus q squared m hat to the 4th times a quantization of the middle term in that A polynomial over on the right, so it starts off with 1 minus q m hat squared plus some other stuff, but there are actually extra terms in here that completely drop out when q is set to 1, plus q q squared 1 minus q cubed m hat to the fourth. M hat to the fourth. So there are a bunch of extra terms here, and there's this horrible extra factor, possibly not so horrible, that multiplies every power of L. That if we had set q to 1, it would simply factor out in the classical limit, and there's absolutely no classical interpretation of it. It's a purely quantum object that comes about when you're trying to quantize this. The wave function for the figure 8 knot takes the form that wave functions generally seem to. So it's e to the minus 2u squared over h bar minus u times an integral of a quotient of quantum dilogarithm functions. And these quantum dialogues are almost hypergeometric. They're non-perturbative completions in the sense of some hypergeometric functions. Let me not say for the moment. I'll give you some properties of them, but let me not say for the moment exactly what they are. Well, anyway, so the wave function is defined as some integral, and it happens to be annihilated by this a hat polynomial. In my last paper, I tried to explain systematically how, given any knot in a closed 3-manifold, one can derive both integral expressions like this for the wave functions and the a hat polynomials. And the basic idea is to cut m, a knot complement, to cut m into ideal tetrahedra. Quantize each of them separately. And then glue them back together. In some appropriate way. Each tetrahedron has a wave function that's a single of these quantum dilogarithm objects. So when we glue them back together, we multiply a bunch of quantum dilogarithms, and then we integrate, essentially to integrate out of our boundary conditions. And a sort of state integral model like this was also described in an older paper with Sergei Gukov, Dan Zagir, and Jonathan Lennels. The marvelous fact is that these wave functions of tetrahedra have S-duality. So phi h bar of p, where p is a sort of boundary condition for the tetrahedron, is equal to phi minus 4 pi squared over h bar of 2 pi I over h bar p. In other words, what I've been calling h tilde, now p tilde. So the wave functions have S-duality, and the gluing is actually completely compatible with the S-duality. So one can very explicitly show that any wave function that's glued from tetrahedra has to be S-dual to itself. And moreover, it's not only annihilated by one a hat operator, but also by the dual operator, which I again had called a hat of L tilde hat m tilde hat q tilde, where these are all the dual variables and shifts. And just to remind you one more time, now that I've defined u hat and v hat, L tilde hat is e to the u tilde hat, sorry, is e to the v tilde hat, which is e to the 2 pi I over h bar v hat, which one can see is e to the I pi du. So it shifts, it corresponds to shifts by I pi, dual to the shifts by h bar over 2. And similarly, m tilde hat is e to the u tilde. So it looks very much like we have something somewhat close to an elliptic function, though this quantum dilogarithm has S-duality, but it doesn't have the very simple transformation for elliptic functions that just corresponds to shifts. I guess that's quite clear in all of this. So there are always a hat-like operators that tell you how shifts act on the various functions. So we have them for Chern-Simons wave functions, and we have them for the wave functions of tetrahedra, and they're much simpler. But still, they're not invariant under shifts. Okay, so if there are no questions, I want to now say a little bit about branes. Yeah, it is. I should just write it. I'm okay with time. So. Okay. So phi h bar p is a product of a ratio of functions. So product from R is 1 to infinity of 1 minus q to the r minus a half, 1 plus q to the r minus a half e to the p over 1 plus q tilde to the 1/2 minus r e to the p tilde. Does that help? It also it obeys the a-hat equations for a tetrahedron. Can be read off directly from this product. So if we hit, so suppose that now L hat is shifting p. So if we hit this wave function with L hat, we get phi, and in fact it should be L hat squared of phi h bar p plus h bar, which is 1 over 1 plus q to the half e to the p phi of p. And similar thing for the bottom. Sorry, so for forgetting who's actually in the audience, this is the thing in motivic wall crossing. It's the what usually shows up is the numerator or the denominator separately. Usually the numerator separately, but you might as well do it with both of them, and it obeys this pentagon relation and so on. So yeah, it's the same function.
Like connections with prescribed monodramy around potential of story.
That's right.
It's cluster variety, and you have this quantum dialogue which appears in the story.
Yeah, it's for the same reason. So there's actually a really beautiful connection.
What was the question, please?
Well, I think the question is if there's a relation to Fock and Goncharov quantization of Teichmuller spaces, and yes, there is, and it's very cool, and it hasn't been written up yet. So each tetrahedron corresponds to one of these quantum dialogues, and as I think you know classically, you take a triangulated punctured surface, and can glue a tetrahedron on top of it to flip the diagonal. And in that sense, if you try to play this game quantum mechanically, if you think of a 3-manifold M, which has a triangulated punctured surface as its boundary, and try to glue a tetrahedron on top of it, and figure out what the transformation should be from the initial Hilbert space to the final Hilbert space, that's the Fock-Goncharov or Fock-Chekhov Teichmuller operator.
So the first thing is the change of triangulation and the Fock-Goncharov.
Yeah.
And the second?
Sorry, that was very quick.
Yeah, that is clear. The second?
So the second is interpreting the flip transformation in 3 dimensions. So we have some triangulated surface here with a diagonal that needs to be flipped, and we glue a tetrahedron on top of it. So the manifold looks exactly the same topologically, but we've done some small transformation in the Hilbert space, and that the kernel of the transformation is the tetrahedron wave function. Cool. And yeah, there are relations to wall crossing which I did not plan to talk about at all. So what I do want to say is a little bit about branes. So first, let me make a very small generalization. I've been talking about SL2C A polynomials, and in fact, when one does mirror symmetry on Hitch and moduli spaces, gauge groups are exchanged with their Langlands duals. So a compact group like SU2 gets exchanged with SO3, and our group SL2C gets exchanged with PSL2C. So one can talk about PSL2 A polynomials as well. And they're in fact very easy to derive once you know the SL2 ones. Classically, we had these L and M coordinates for the phase space of SL2 theory. So the SL phase space had LM coordinates or UV coordinates. The phase space for PSL theory can also be described in terms of these, but they're not really good coordinates. So let me put tildes on them because they correspond to the dual group. But in fact, the good coordinates are twice these. So I want to use a U tilde that's 2 times little u tilde, and a big V tilde that's 2 times little u tilde, and a big M that's M squared, and a big L that's L squared. Then the PSL2A polynomial as a function of L tilde and M tilde is just 2 copies of the SL2A polynomial. You want something that's invariant under changing the sign of L. All of the A polynomials for knots in S3 already depend on M squared, so changing the sign of M doesn't do anything. So all we need to do is multiply the SL polynomial at minus LM times the SL polynomial at Ln. And then it's a function of M squared and L squared, and we can do these substitutions and get the PSL polynomial. So likewise, we can do this quantum mechanically as well. A hat factors the same way that A factors. So there's an A hat tilde for PSL2, which will depend on 2 operators, L tilde hat and M tilde hat, which is some operator L tilde hat times, so it's some prefactor corresponding to a quantization of that prefactor in the classical case, times A hat of L tilde hat M tilde hat Q tilde. Where H bar tilde now is, I haven't made a claim about S-duality. H bar tilde or Q tilde now is simply the quantization parameter for the theory with the dual group. Though, of course, the claim I want to make is that S-duality exchanges A of LMQ with a hat with a tilde of L tilde M tilde Q tilde. So there's a left factorized structure like this, and in fact, the left factor does absolutely nothing. And the wave functions, once you analytically continue, the wave functions for SL2 and PSL2 are identical. So as far as I can tell, for all intents and purposes, you can just ignore that. And the relevant part is this one, and that's the duality that I've been talking about. It exchanges A with A tilde. Okay. Right. So branes. I want to look for branes that are cut out by A polynomials in the Hitchin moduli space. So this is, in a sense, a toy example of what you can do with mirror symmetry, but it's simple and concrete, and I kind of like it. So consider the Hitchin moduli space for the torus. So M flat SL2C T2. So this is that phase space of SL2C Chern-Simons theory, and it's in fact a hyperkähler manifold. Topologically, it looks like R2 cross T2 mod Z2, where these are the magnitudes and T2 are the phases of the eigenvalues L and M. And it fibers over a base, and the best way to explain the base is R2 mod Z2. And I can put coordinates on it, B1 and B2, where B1 is the real part of U, B2 is the real part of V, and there are coordinates on the fibers for the imaginary parts of U and V. Sorry, F1 and F2. And of course, the Fi's are 2 pi periodic. Okay, so generically, the fiber of this moduli space is a torus, though it degenerates exactly at the origin into a so-called pillowcase. So at 0 in the base, the torus becomes T2 over Z2, which, draw a little bigger, which looks like that.
This is for nilpotent Higgs bound?
Yeah, so you always have to add some stability conditions. But here, I just want to think of it as flat connections on the torus. Flat complexified connections on the torus.
But 0 is where the Higgs field is nilpotent, 0 eigenvalue. Yeah, exactly. So the base, so doing this in terms of Higgs bundles, the base is parameterized by the Higgs field, and exactly. Thanks. So MH is hyperkähler, meaning it's got 5 minutes to present itself. So it has 3 complex structures. In which the holomorphic coordinates, the ones, so this is, I believe, identical to Hitchin's notation. So in complex structure J, it's the one where the complex structure is naturally induced as, from its definition, as the moduli space of complexified connections. So the complex coordinates here are U,
which was b1 plus I f1, and v, which is b2 plus I f2. And in complex structure I, the base and the fiber are each holomorphic. Right, so, and K is ij. It has three real symplectic forms, omega I, omega j, and omega k. The real symplectic form in complex structure J, which we're actually not going to use, is db1 wedge df1 plus db2 wedge df2. The one we are interested in is the holomorphic symplectic form in complex structure J, which is omega I minus I omega k, which is exactly our dv wedge du. So we want to take an A polynomial for a knot, define an A polynomial defined by a three-manifold M, and use it to cut out a Lagrangian brane. So we want this Lagrangian, 0 locus of A ln equals 0. And it's fairly clear that this is a holomorphic condition in complex structure J. So it defines a B-brane in that complex structure. On the other hand, it's this A polynomial, as I've described it in Chern-Simons theory, was Lagrangian for the holomorphic symplectic form in complex structure J, which means that it's Lagrangian with respect to omega I and omega k. So it defines a Lagrangian A-brane here and here. Or in other words, it's more compactly, it's an AB A-brane. We'd like to S-dualize the brane. Following Kapustin and Witten, S-duality is supposed to correspond to mirror symmetry followed by a hyperkähler rotation.
So what is it? Is it torus or S2 in this vibration?
Sorry?
Is it torus or it's a S2 in this vibration?
Is what, the brane?
Elliptic vibration, the M Higgs. And so how does it work? So
it wraps one direction in the base and one direction in the fiber.
okay.
And I hope to do a very simple example before time runs out. So we want to S-dualize this, which means that we apply mirror symmetry, which takes an ABA brane to an AB brane, and then we do a hyperkähler rotation, which exchanges complex structures or rotates complex structures J and K, and gets back to an ABA brane. So simply by putting letters on the board, it looks like we start with something like this and get an object of the same type. It is an object of the same type. It's going to be an A polynomial, except it's not going to be an A polynomial in the same Hitchin moduli space. It'll be an A polynomial in the Hitchin moduli space for the dual gauge group, for PSL2. And both, so M Hitchin tilde for PSL2 and M Hitchin both fiber over the same base. And the relation on the base is that essentially the real part of U is going to be identified with the real part of U tilde, and the real part of V is identified with the real part of V tilde. On the fibers, if I write them in terms of little U tilde and little V tilde, for PSL2, the periodicity is only pi, whereas it was 2 pi over here. So to make the story quick, well, let me do an example. Simplest possible one. Let's do the unknot. So the A polynomial is L minus 1. That means that in terms of coordinates on the base, it wraps definitions are a little bit funny. So V is fixed and U is allowed to vary, which means that it wraps one direction on the base, the B1 direction, and it wraps one direction on the fiber, the F1 direction. And it's fixed in the other two. And then as Eric so elegantly said yesterday, mirror symmetry is really just T-duality. So geometrically, this Lagrangian turns into a brane described by conditions B2 equals 0, or B2 tilde equals 0 now, and F1 tilde equals 0. And then we do a hyperkähler rotation. So B2 is still 0, but now F2 tilde is 0. So the hyperkähler rotation acts on the fiber and exchanges F1 and F2. And what we get at the end of the day is a very simple thing. We get back A tilde is L tilde minus 1, which, as predicted, is little l tilde minus 1, little l tilde plus 1. So one can do exactly the same thing for the trefoil, and it works the same way. The trefoil is still one direction, and a line in the base and a line in the fiber. They're slightly tilted lines. And the kind of cool thing is doing it for the figure-8 knot, or much more complicated A polynomials. And then what you do is look at the amoeba of the A polynomial curve. So project it down to the base. Mirror symmetry does absolutely nothing in the base. So in this mirror symmetry or T-duality transformation, you just get tildes on base coordinates, or if the curve is more complicated, its projection to the base has to stay the same. So for the figure-8 knot, its projection to the base is something like this, and it turns into the same thing down here, except effectively in the capital coordinates for PSL, the thing is scaled by a factor of 2, and so you have to try to guess which polynomials could possibly fit an amoeba that's scaled up by a factor of 2. One answer that certainly works is the product of the SL polynomial times itself at minus L. And there's not much more freedom to get anything else. You can play around with phases and signs a little bit, so they're not completely fixed. But it's certainly compatible with an SL A polynomial mirroring to a PSL A polynomial, and vice versa. So that's the basic story. That was a toy model. So it's an example of what mirror symmetry can do for classical A polynomials and classical Chern-Simons theory. Much more interesting question is how mirror symmetry explains duality for quantum Chern-Simons. How it acts on the Chern-Simons Hilbert space in analytically continued theory, or the wave functions. And there's been lots of progress, and I hope there will be a complete answer soon. Thanks. Sorry for that.
Questions? Richard?
So is there anything?
Excuse me.
Is there any relation between this Chern-Simons with complexified group and holomorphic Chern-Simons on the cotangent bundle of the manifold of the 3 knot?
Not as far as I know, but there may well be. And if you had any thoughts on it? Yeah, I don't know. Not obviously.
Any other questions?
Does this Z have any sort of name in mathematics?
No, I mean it doesn't. So it doesn't have a name in the sense that Jones polynomials do. It's a topological invariant of a three-manifold, but it's only been discussed in a handful of physics papers so far. It's actually, so you can think of it as the analytic continuation of the Jones polynomial. So the reason mathematicians are interested in this, the reason not theorists are interested in this, is because it has the same asymptotics as the Jones polynomial, so you can use it to analyze things like the volume conjecture.
More questions? If not, let's thank the speaker again.